Hello, everyone. Um, Welcome to this talk. Today's talk's subject is exploring hardware-software co-design methodology. I'm Farhan Shafiq. I'm from the Heterogeneous Compiler Lab in Huawei, Canada. So there are a few pain points in hardware-software co-design which have been known for a while now. Initially, as we have more and more innovation in hardware design, the time to market requirement gets tougher and tougher. Similarly, as you have more innovation, the complexity of the hardware and software tools related to it with each generation increase with more complex designs. And developing these tools requires a lot of manual effort, which is prone to delays and errors. So the first thing that we have to look at is instruction set architecture design. And basically, there are a few basic challenges that you have with ISA design. Of course, complexity of requirements is there, but also it's not just the ISA, but there are a lot of hardware and software components which are impacted by the ISA design. This includes your simulators, compilers, profilers, your synthesis tools, and performance libraries. So the conventional way that ISA design has been done, you have multiple sources of ground truth where you frequently have different versions and inconsistencies across the different versions of your ISA. More often than not, it is in the form of Excel sheets or sometimes some kind of language. But because of having these multiple versions and many different teams interacting with this description, you a lot of the times will see multiple interpretations from the different teams. And because your description is informal and not verifiable, it is very difficult to agree on or develop a single understanding of the description. And so this requires a lot of tedious and manual work as well, because with every iteration of your ISA, you have to upgrade the tools to your new ISA version, as well as the descriptions of those ISA need to be updated. So we have learned from a few experiences with some of the Huawei chips that we have built in-house. So for example, some observations from an AI chip that we developed before, we had multiple generations of the chip architecture which were designed, and the design periods for different generations overlapped in time. There were major changes in architecture and ISA between multiple generations. Then you have multiple variations even within the same generation, because you have versions that are targeting cloud, mobile, or IoT space. So you have different ISA subsets for each target. And also your hardware resources are different because your performance requirements are different. And then the ISA is very complex. You have more than 200 instructions, scalar, vector, matrix, DMA. You have very complex instruction encoding semantics. You have special instructions which have complex semantics, as you would expect with any neural network accelerator. And a lot of the effort that we saw went into toolchain development and maintenance, because you have your simulators, functional and cycle accurate, you have assembler, disassembler, and the compiler backends. Another chip that shall not be named, also we had a few observations. So if we look at this graph over here, on the x-axis is the timeline and on the y-axis is the ISA versions. And what we note that the software development starts very early, as soon as we have the 0.1 version of our ISA. And also integration, compiler and functional simulator tests are way before any major ISA release. If we look at these different dots, these are releases of ISA, and we don't get to version 1 until very late, to be specific, after 2023 ISA iterations. So this kind of iterative development across compilers, simulators, your RTL testing continues as these ISA iteration comes up. So to mitigate these issues that we observed over the design cycles of previous chips, we decided to design a retargetable hardware-software co-design SDK. And the goal of this project was to develop a Huawei home-built framework which can auto-generate a software development kit from a semi-formal single-source description of ISA. And to do that, to achieve that, we first had to design an architecture description language, short for ADL, which includes your ISA encodings, assembly info, architecture state, and some instruction semantics, being the primary components. And then we also could include a library of common components, which could include instruction constraints, some kind of analytical performance modeling capability, and also high-level RTL modeling. This can then be used so first a parser will use this description and generate an internal IR. This IR is then used by various tools that have been developed to process this kind of IR to generate assembler, disassembler, ISA markdown documents, functional simulator, analytical performance model, cycle accurate simulator, compiler, auto test generator, and profiler debugger. Of course, some of these components are already functional, but some are either still under development or part of our future work. One thing that I would like to highlight here is that the utility design preference and language primitive semantics have been kept separate from the whole flow over here to make sure that the same ADL could be used to target different preferences and different languages. So the ADL was designed based on a few principles. First of all, a retargetable ADL needs to be descriptive enough to represent various ISA types, for example, variable and fixed instruction widths. Then another key point that we wanted to make sure was to do a top-down hierarchical representation of ISA rather than a very plain representation. So basically what that does is it gives you a concise representation, and it makes it easier to visualize, modify, and verify across different teams, and also make it easy to share with other teams. And then the third key point was to isolate machine description from tools preferences. So basically, what that does is it enables hardware designers to write the description without having to worry about the tools part. Whereas if we look at the LLVM table chain, which mixes hardware description with compiler design preferences, this can be written only by the compiler developers and is a tall order to ask architecture folks to start writing this for us. And then the last point is to separate backend implementations from the language itself. So to achieve that, we use an IR, which represents your ISA, which has been modeled by ADL. And then once the code is parsed and you have your IR, you can reuse it for different backends. So the tools that generate compiler or simulator or markdown. So a simple example of how the ADL would look like or does look like with some RISC-V examples. So basically, your instruction set description consists of two sections, decode and operation. The decode section gives architecture-specific encoding information, whereas the operation section gives you the information for each instruction's operation. There's a separate entity which is called record, and this defines the tokens which are used in decode and operation sections. So as an example, we have this example of a few RISC-V instructions being defined in the ADL. And so the decode section, as we can see, describes the encoding, whereas the operation section tells us about assembly and how the operation works. So so we can see the set ASM, set description, set behavior. Obviously, the set description part would be used to generate markdown, for example. And of course, the record part here is defining the tokens which are used within these two components. So once we parse the ADL, we generate the intermediate representation, and we can symbolize it in the form of a graph, which can be used across different teams for visualizing, for discussing, and also verifying that the encoding that has been written is true to the intent. So how do we use the IR to auto-generate functional simulation? Well, ADL allows you to have the instruction behavior directly written in C code, and the semantic description language, which I'll get to later, is coupled with a behavior expressed in C. So this can be used to have an auto-generated simulator directly from the ADL, either through the semantic description languages, coupled C behavior, or the directly written C behavior. So this can be used to have an auto-generated simulator directly from the ADL. However, since there are also alternative existing simulator generator frameworks, we did use ArcC to generate a simulator for our ADL. So essentially, in that case, what you do is you just generate the files which are needed by ArcC to generate a simulator. Then comes the more challenging and exciting part of the tools, which is the auto generation of compiler backend. And so basically what happens is that once you have your IR, the compiler backend generation will use that IR to generate a few backend files independent of other input files. So what I mean by that is, if you have the IR and you have the architecture state, we are able to generate some of the backend files. So here, as an example, I show the TD files for the LLVM backend, and we have instruction formats, instruction info, target, and register info being generated from these two alone. What I do want to highlight is that the instruction info TD file does not contain any patterns. Then the ADL needs to be augmented with a semantic language IR, which I will get to in the next slide, and also compiler IR mapping. So whichever compiler we are generating for, we need to write a mapping between the semantic language IR and the IR for the target compiler. And then some details of microarchitecture state and ABI give us the ability to generate instruction info patterns, calling conventions, and schedule. So a little bit more about the semantic description challenges. So essentially, a formal description of ISA semantics is needed for auto generation of instruction selection, because you need to be able to reason about the semantics. However, there is a lot of, well, not a lot, but there is a few semantic descriptions that are out there which can be used for formal semantics, formal verification rather. And however, the key point for ADL is to be simple and intuitive enough for ISA architects, but also be able to use it for compiler generation. So to achieve this, we defined a generic IR library, which is generic enough to represent various machine operations while being very close to LLVM GMIR. So it can be correlated with compiled codes IR. And so we described the RISC-V base ISA using the library, and selection patterns were generated from that. So of course, we faced a few challenges while doing that, which include the compiler pseudo instructions, because once you're going from ISA towards the compiler, you don't have any information about compiler pseudo instructions. And similarly, any target-specific multi-class patterns in case of RISC-V, the load store, and any complex instruction behavior which cannot be modeled using the generic MIR. So this brings us to the last part of the challenges, which is being able to do performance modeling effectively. So there's a few observations on that, which is system performance is a function of both hardware and compiler. Hardware design space exploration usually would be conducted in isolation, and you would usually look at theoretical performance, but performance of real application is often different from hardware theoretical peaks. So how to mitigate that? You could do cycle accurate simulation for thorough evaluation, but it is impractical because of the huge time requirement. And given how huge the design space is, it becomes totally impractical. Because if we look at the hardware design space, you have so many moving parts. You have your memory hierarchy, you have processing elements and functional units, various variables about your network on chip design or your bus design. You have power management, messaging, and sync. If you come to the system software optimization, you have a lot of compiler optimizations that need to be taken care of, and are undefined at the time of hardware design exploration. And similarly, runtime schedulers have a huge impact on your performance. So we tried to explore any AI-based approaches to performance modeling. There's quite a few researches that have surfaced recently, which look at different aspects of performance modeling. You have predictive hardware design exploration tools, a few interesting papers over there. Then you have machine learning-based cross-architecture performance prediction, ITML being one of the really interesting work in that area. Then you have machine learning-based network on chip performance prediction. You have also some work going on using AI for guiding compiler optimizations. And then also predictive ML-based auto-tuning. So learning from these different works, we have tried to come up with a vision of having a predictive performance modeling framework, which is enabled by AI, which uses compiler in the loop of the core design. So if we look at this blue box over here, this is our AI-enabled predictive performance framework. And on the right side, we see this design cycle of the hardware design space exploration. And on the left side, we see the design cycle of the compiler tools. So For the hardware design space exploration, it works as a only inference, where your performance, where your design space is your current design point is encoded in ADL, and automated tool generation through the RSDK is used to get your software tools. Your performance prediction model over here gives you an estimate on your design's performance, and feeds it back into the design space exploration framework. Of course, this prediction then comes back and helps you refine your hardware design, and you can iterate multiple times where your design space subspace will converge on every iteration. On this side, you have two things going on. You have inference, but also training going on. So from inference perspective, your performance prediction framework helps your auto-tuning framework to optimize your compiler optimization space. But at the same time, the compiler gives you a program IR or a target architecture's binary, which then run on reference cycle accurate models, which are manually developed to give you some performance stats. And both of these are fed into the performance model training framework over here, which refines your performance model more and more, and makes it accurate. This is a work in progress, or rather a work in the earlier stages, but we are hoping to see some positive results from this effort. So that's all for my presentation today. Thank you for listening, and thank you for your time, and I hope to hear any questions or feedback you may have for me. Thank you very much.